Okay, let's continue our discussion. Till now, we have found Euler-Lagrange equation, and with two boundary conditions, we know y of x at x1 and x2. Let's solve an example for this equation. We have introduced Burkitt-Cron problem in the first session, which was the path. In this path, we have which is the vertical path, in which path we have the minimum amount of time for a mass to slide from point 1 to point 2 with initial velocity v1. We have formulated the problem as follows. Y of x is the path of the mass. Let me draw it. This is point 1 and this is point 2. We know x1 and y1. We know x2 and y2. There is a frictionless path between point 1 and point 2. Let's name it y of x. There is a mass with initial velocity v, with initial velocity v1, which slides through this path. We want to find the path. Y of x is unknown. We want to find y of x in order to have the minimum amount of time for the mass m to travel from point 1 to point 2. We have shown that this time can be calculated by this formula, where as it can be seen, it is integral from point 1 to point 2, 1 plus y dash by 2's squared, or root of 1 plus y dash by 2's over v1 by 2 minus 2g multiplied by y minus 5 y1, all of them by 1 over 2. This is the problem. In this problem, we are going to find y of x in order to minimize the amount of y. Let's focus on a special case when initial velocity is 0. So we can say if v1 is 0, and we can also put the origin of the problem. We can put the origin point at any arbitrary point. It doesn't change the problem. Let's put the origin at point 1, so we can say that y1 is equals to 0 and v1 is equals to 0. So we can rewrite the problem as follows. This is the problem which is going to be minimized, and function f is the function we will use in the Euler-Lagrange equation, since 1 over roots of 2g is a constant number, so we can say f in the Euler-Lagrange equation can be presented by this formula. And if we use Euler-Lagrange equation as we have seen in the previous slide, let me show you. Derivative with respect to x of partial derivative of f with respect to y dash minus partial derivative of f with respect to y equals to 0 if we replace f as by this formula in the Euler-Lagrange equations and do the derivatives. We will obtain the following ordinary differential equations. As we can see, this equation is the second order differential ordinary differential equation, and to solve these equations we need two boundary conditions, y1 at x1 and y2 as at x2. In order to solve these equations, we need to remind our BSc courses about ordinary differential equations. In these forms of equations, when we don't have independent variable x in the equation directly, we can rewrite the equations as y triple as a function, as y dash as a function of y if we reintroduce u, if we introduce variable u equals to y dash, then we can say y double dash is equals to let me show you y double dash. Let's rewrite it here. Y double dash is equals to, as we can see in this problem, u prime or u dash, u prime is equals to d of u over d of x. We multiplied d of y and divided by d of y. In this problem, d of y over d of x is equals to y dash, or it's equals to u. So we can say that y double dash is equals to u multiplied by derivative of u with respect to y. So we can say that we can express u as a function of y and rewrite the above equations as follows: u derivative of u with respect to y equals to minus 1 plus u do, all of them over 2y, and by collecting all of u parameters in the left hand side and collecting all of y parameters in the right hand side and integrating them, we can reach to these equations. It can be easily done. You can do it by yourself. Y multiplied by 1 plus u by 2 is equals to C1, and we then rewrite u as y dash, and then we have I'm sorry. Okay. And then if we rewrite the equation, we have the following equation: x is equals to integral of these equations plus x0. We can integrate these equations by the change of parameters. If we say y is equals to C1 sine of t over 2 by 2s, and replace them in the following equations. We reach to these equations, and by integrating these equations we have x and y as a parameter of t, where t is the curve parameter, and as we can see, this is a cycloid curve from point x1 to point x1 and y1 to point x2 and y2. Okay, now we reached to the end of the class. In this session, we found Euler-Lagrange equations, and we solved an example by using Euler-Lagrange equations. In the next session, I'm going to speak about the delta method or the variation method. Hope to see you soon. Bye bye for now.